At 4:15 on August 9, 2025, something unusual lifted off from Ukrainian territory. It was a single unmanned aircraft, moving without lights, without signals, and without any hint of where it truly came from. Within minutes, commanders on both sides realized they were watching a flight that did not follow the rules of modern war. No radio link, no GPS trail, no electronic signature. Just a slow, steady path toward a destination no one could confirm yet. What began as a quiet takeoff soon exposed the limits of even the most advanced air defenses and raised new questions about how battlefields are changing. And this flight was only the beginning, because what happened next forced every military analyst to reconsider what is possible. To understand why this single launch mattered so much, we must look at how and why the mission started. At about 4:20 on August 9, 2025, the Ukrainian strike aircraft crossed into Russian airspace and entered what was supposed to be the first major bottleneck, the Russian GPS suppression zone. Russia had deployed the Pol 21 system, a large mobile jamming installation built to wipe out GPS and other satellite navigation signals for anything flying or driving in its area of effect. For the pilotless aircraft, this meant that every usual path of remote control or satellite guidance was cut off. Engineers on the Ukrainian side had designed the mission so the drone would not rely on GPS at all, which meant the jamming that Russia counted on immediately became irrelevant. The first test of Russia's system came when the drone passed through the 20-kilometer jamming bubble generated by Pol 21. The ground-based antennae emitted thousands of watts, enough to drown a weak satellite signal in the L-band by orders of magnitude. At that point, the UAV's internal navigation system registered a brief wobble. Its inertial sensors recognized the loss of external references, but instead of spiraling into a search pattern, it held its course. The Russian operators expected automatic lost link behavior or break to safe mode, but the drone ignored all that. The secret was the method of guidance. Instead of relying on satellite signals or remote commands, the aircraft used terrain recognition and fixed infrastructure. During mission planning, the route had been mapped to run along the M3 highway, past the distinctive S-curve near Selzo, followed the power line corridor, crossed the three-span bridge, then tracked the riverbank until the warehouse complex came into view. In effect, the drone navigated like a vehicle on a predetermined road, not like a guided missile adjusting to radio commands. Autonomous vision and inertial systems handled this path. By the time the jamming bubble had been exited, the UAV had bypassed the main branch of electronic defense without broadcasting a single signal. Next came the spoofing attempt. The Russians activated a suite of systems intended to trick any GPS receiver into believing it was somewhere else. Commands such as return to home, enter hover mode, or manual override were flashed by the jammers. The logic was, if we cannot jam you, we'll force you to navigate into a trap. But the Ukrainian drone had no GPS receiver, no data link antenna, and no RF command port. It simply ignored all fake commands because there was nothing inside to receive them. That meant the millions spent on layered electronic warfare on special forces, anti-drone jamming vehicles, and command stations saw no effect at all. For Russian defenders, this represented a moment of shock. Their doctrine was built on denying satellite navigation, then forcing the attacker into predictable behavior. But here, the attacker had refused to behave. The implications were huge. If one UAV could bypass the best GPS jammers, then any defense system counting on jamming rather than destruction or interception was now vulnerable. The logic underpinning years of investment in navigation warfare was suddenly exposed. By the time the drone was well inside Russian territory and over the final approach corridor toward Alabuga, it was operating in full silence. No signal, no remote link, no GPS beacon, nothing. It was immune to denial, immune to deception. Russian counters were not built for that model. They were built for an enemy that still listened. And so the drone arrived at its target without alerting in the way anyone expected. But even after the jammers and spoofers had failed, the journey was far from over. The real challenge was getting past Russia's best radar and air defense systems. Russia's electronic defenses came online minutes after the Ukrainian drone crossed the border, and the first system to react was Pol-21, a large GPS jamming network designed to blind anything that relied on satellite signals. According to NATO reporting, Pol-21 broadcasts up to 1,000 watts of interference power, which is strong enough to drown out the very weak GPS signal that normally reaches Earth at around minus 130 decibels per milliwatt. Because of this power difference, Russia believed any unmanned aircraft inside the 20-kilometer jamming bubble would immediately lose its navigation link and fall into a holding pattern. Russian planners built their doctrine on the idea that most drones still depend on GPS or GLONASS, a system similar to GPS that is operated by the Russian government. The drone entered this jamming area at about 6:34, and Russian operators expected it to fail almost at once, yet what they saw was completely different. The moment the aircraft met the interference zone, its body made a small wobble, which suggested its internal sensors recognized the change in signal strength. Under normal conditions, an unmanned craft would begin searching for a new signal, and if it found none, it would either return to its launch point or circle until it ran out of fuel. Military training manuals describe this as lost link behavior, and it is common across most NATO standard drones. Instead of reacting in that predictable way, the Ukrainian aircraft steadied itself and kept its original heading, surprising the electronic warfare crew watching their screens. The reason for this unusual reaction becomes clear once you understand the guidance method used in the mission, because the aircraft did not rely on satellite navigation at any point. Ukrainian engineers had prepared a route based on visible terrain, so the drone followed highways, power lines, river curves, and bridges to read the landscape just as a person reads a map. Modern research shows that drones can navigate by matching real-world images to stored photos, and several universities have demonstrated this in GPS-denied flight tests. Landmarks such as the S-curve near Selzo or the three-span bridge were chosen because they are almost impossible to spoof, meaning electronic noise cannot change them. Once the drone recognized these points, it moved to the next marker in its memory, creating a stable path that did not depend on radio signals. This type of terrain-based navigation explains why the Russian spoofing effort also failed, because spoofing simply sends false satellite signals to trick a drone into changing course. Russian forces attempted to broadcast fake GPS coordinates and override messages, including return to base, land now, and switch to manual control. These commands came from the Repellent series counter-UAV systems, which Russia often uses for close-range protection. Technical notes from Russian defense sources claim these units can transmit thousands of automated instructions within seconds. However, none of these signals reached the Ukrainian craft, because the drone had no hardware installed to receive them. Its antennas, receivers, and data link modules had been removed before the mission, so the aircraft behaved like a sealed system that could not hear anything around it. The complete failure of the spoofing cycle revealed a deeper problem in Russia's jamming doctrine. For years, Russian strategy assumed that every drone depended on some type of radio link, and that taking that link away would force the aircraft to behave predictably. When the Ukrainian drone ignored both jamming and spoofing, Russian defenders realized their layered electronic defenses were designed for a different era. Analysts in the United States and NATO have noted that such a failure shows a major shift in modern warfare, because cheaper autonomous aircraft are now able to defeat expensive electronic systems. If this continues, future conflicts may see a move toward dumb smart weapons, which are simple in design but almost impossible to disrupt. The incident also sends an important message to global militaries, since the cost difference between offensive and defensive systems has grown sharply. Russia spent millions of dollars building Pol-21 and similar networks, yet a single low-cost drone crossed the entire region without reacting to any of it. Defense planners in the United States, Europe, and Asia will likely review how their bases, supply depots, and command centers are protected, because jamming-focused tactics may no longer work against autonomous platforms. In the long term, armed forces may need to redesign their air defense layers to stop threats that do not depend on electronic signals at all. Yet even without GPS, the drone still had to slip past Russia's most advanced radars, and this became the next major test of the mission. Russia's long-range radar network finally spotted the Ukrainian drone when it climbed to clear a ridge at around 9:45, and this moment marked the first time the air defense crews saw a clear radar contact. The system that detected the drone was the 92N6E Gravestone radar, which forms the main tracking element of the S-400 air defense complex. According to data published by the Russian manufacturer Almaz-Antey, this radar works in the S-band, 2 to 4 GHz, and uses thousands of transmit-receive modules to search for aircraft at long distances. Under normal conditions, it can track a fighter-sized target at up to 250 kilometers, but that range drops sharply with small unmanned aircraft. NATO's research on radar physics explains that detection range decreases with the fourth root of radar cross-section, meaning a craft with 1/6. The signature of a fighter may only appear at 1/3 of the normal range. That is why the Ukrainian drone only appeared at 89 kilometers, just long enough for the operators to register an anomaly. The drone disappeared again when it dropped to 50 meters, because this low altitude placed it inside an area known as ground clutter, a space where radar waves bounce off trees, buildings, and terrain features. Air defense manuals note that ground clutter creates a heavy noise pattern on radar screens, and small drones often vanish inside this layer due to weak reflections. When the Ukrainian aircraft returned to a low altitude, it blended into this noise band, and its radar signature became almost impossible to separate from the background. The operators could still hear routine messages on their radios, but the bright contact that appeared just seconds earlier faded into the clutter, which made the situation confusing for the team watching their displays. The timing of this radar loss became even more dangerous because it happened near 10 o'clock, when the overnight crew was about to hand over the station to the day shift. Military readiness studies show that shift changes often create a short period of lower awareness, since one group is preparing to leave while the next group is not fully synchronized. For about 15 minutes, this gap can slow reaction times, and in this case, the Ukrainian drone passed through the most sensitive part of Russian airspace exactly when attention was split. The night team logged the short radar contact but hesitated to treat it as a serious threat, while the day team did not review the entry until the object was already far beyond their sector. Another obstacle came from the Panzer S-1 systems guarding the same region, because these vehicles combine missiles and rapid-fire guns that protect the S-400 from close-range threats. However, the Panzer turret has a mechanical limit and cannot aim its cannons below -5 degrees, a detail confirmed in the system's technical description from the manufacturer KBP. At a distance of a few kilometers, this angle leaves a blind zone under the guns, and the Ukrainian drone was flying exactly inside that space. Since it held an altitude near treetop level, the Panzer units could not fire without raising their barrels above the drone's position. This design gap, which Russian engineers built into the system to protect the turret mechanism, created a tactical weakness that the drone crossed without facing any fire. When the crews looked back at the radar log later in the morning, they saw the earlier entry but assumed it was a false echo caused by morning air temperature changes, something radar operators often see at sunrise. Defense analysts explain that warm air over cold ground can create temporary reflections, and inexperienced crews may downgrade these contacts as routine interference. By the time the day team confirmed the contact was real, the unmanned aircraft had moved at least 40 kilometers past their position, leaving them with no practical chance to track it again. This sequence of events showed a deeper cultural issue inside the defending force, because many militaries struggle with environments where operators fear making the wrong call more than they fear missing a threat. In situations like this, a radar contact that appears unusual may be set aside instead of escalated, especially when the team is already tired after a long night shift. The Ukrainian drone moved forward because hesitation and procedure slowed the defenders more than technology did, And this pattern repeated across multiple sectors as the aircraft flew deeper into Russian territory. And this brought the drone to Russia's final defensive layer, the systems built specifically to stop unmanned aircraft of every size. The Ukrainian drone entered its final approach toward Alabuga shortly before 11:40, and by this point Russian warning messages had already moved through several command posts, including Bryansk and Nizhny Novgorod. Operators in these regions sent repeated reports describing an unmanned aircraft that ignored jamming and followed a steady course toward the Shahed production center. However, despite these alerts, no effective action was taken in time because the early reports were marked as moderate confidence, which slowed decision-making. Studies on command behavior in electronic warfare show that uncertain signals often lead to delayed responses, especially when commanders expect remote-controlled drones instead of autonomous ones. While local units tried to align their systems, the aircraft kept closing the distance without facing any real resistance. The first major defensive system to react was Repellent 1, a Russian counter-UAV jammer designed to force hostile drones into safe modes. According to technical data released by Russian state exporter Rosoboronexport, Repellent 1 can send over 10,000 automated commands in just a few seconds in an attempt to override a drone's control system. At around 11:47, the system released this full protocol attack, sending instructions like return to base, land immediately, hover mode, and switch to manual control. These commands are usually effective against commercial drones, and even some military variants, because they exploit the control software that expects operator input. In this case, though, the missiles and antennas fired their signals into empty space, because the Ukrainian aircraft had been built without any radio receivers. It flew like a sealed machine, unable to hear even a single message sent toward it. Russian forces then switched to frequency-hopping attacks, hoping to catch the drone between internal cycles. This method works by striking multiple frequencies within microseconds, which can disrupt encrypted military links and temporarily confuse advanced navigation computers. The U.S. Air Force notes that frequency-hopping jamming is commonly used to break through hardened links found on aircraft and guided munitions. But the Ukrainian drone did not rely on any link, so the rapid-fire interference had no effect. It simply continued on its straight path, and the Russian crew watched their screens as every expected reaction failed to appear. Next came the spoofing walkback maneuver, which is considered one of the strongest tools against satellite-guided drones. The technique works by creating a fake GPS position far from the real location, then slowly walking the coordinates back toward a chosen point to force the aircraft into a controlled turn. The method has been used by several militaries to capture or redirect unmanned vehicles in conflict zones. A documented example occurred in 2011, when Iran claimed to have diverted a US RQ-170 drone by spoofing its navigation signals. The Russian operators tried a similar process here, but the result was identical to the earlier attempts because the craft had no GPS hardware inside its frame. The signals passed through the air, but no internal component existed to register them. As the drone moved closer to Alabuga, Russian units activated full-spectrum barrage jamming, which involved 14 different jamming stations broadcasting noise across a range from 100 MHz to 6 GHz. A field manual from the U.S. Naval Research Laboratory states that such broad-spectrum interference can overload processors by inducing electrical noise inside the circuits. Russian planners expected at least some internal disruption. However, the Ukrainian aircraft had been shielded by a Faraday cage, a layer of metal that blocks electromagnetic fields from reaching sensitive components. The processors inside continued functioning as if no jamming existed at all. All of these failures came together in the most important realization that Russian crews reached around 11:50, only minutes before the strike. After running through every possible countermeasure, operators began comparing their logs and discovered that none of their systems logged a single response from the aircraft. Analysts reviewing the data understood that the drone did not carry any radio-based equipment, not a single receiver, not a satellite antenna, not even a fallback emergency channel. It was completely air-gapped. Because of that, it could not be hacked, redirected, confused, or stopped by any electronic method. The entire electronic warfare network, built at great cost, was designed to fight drones that needed communication, but it had no answer for one that did not listen at all. What happened next shocked even experienced analysts and changed the conversation about future warfare. The drone began its final attack run at 11:52, and its flight computer shifted from navigation to strike mode, sending the aircraft into a fast terminal dive. The unmanned craft cut straight through the anti-drone mesh around the Alabuga complex, because the barrier was designed for light quadcopters, not a heavy airframe moving at nearly 180 kilometers per hour. This speed matched the figures seen in several military trials involving large fixed-wing UAVs. Inside the building, the thermite charge activated on impact. Thermite burns through a chemical reaction between iron oxide and aluminum, producing temperatures above 2,500 degrees Celsius, which is hot enough to melt steel roofing. The molten stream ignited fuel stored inside the Shahed units, creating a chain reaction that destroyed thousands of drones in less than 30 seconds. The fireball climbed to almost 800 meters, and initial damage estimates placed the financial loss near $500 million, based on the cost of Iranian-built Shahed airframes reported by defense analysts. This strike severely reduced Russia's long-range drone capability, and it also damaged the image of an air defense network often described as impenetrable. For the United States and NATO, the lesson is clear. Jamming-based defenses are no longer enough, and future systems must be designed to stop drones that do not rely on electronics at all. Countries like China, Iran, and Turkey are already studying this event, and many analysts believe it will trigger a new global race to build fully autonomous strike platforms. And all of this began with a single takeoff many thought would lead nowhere. The August 9th strike on Alabuga ended with a message that Moscow could not ignore, because a single unmanned aircraft slipped past every Russian defense layer and destroyed months of Shahed production in less than 60 seconds. This happened after Russia spent years promoting its air defense network as one of the strongest in the world. Yet the drone proved that a silent machine without GPS, radios, or data links could still defeat it. Reports from the CSIS missile database confirm the value of the destroyed drones at nearly $500 million, while research from RAND shows that electronic warfare cannot stop autonomous platforms that carry no receivers at all. For the United States and NATO, the lesson is simple. The next battles will be shaped by low-cost systems that do not respond to jamming or spoofing, and Russia's vulnerability is now clear to everyone. If you want more deep analysis on modern warfare, remember to subscribe to Military Force so you never miss the next report.